that we know a little bit more about alkenes. We refreshed our memory on their construction or their anatomy, combination of sigma bond and pi bond. The pi bond is weaker, and our preview lecture to this particular topic introduced that idea that the pi bond is special. And so we're going to talk now about the reaction of alkenes plus strong acid. And the strong acids we're going to use in this case are HCl, HBr, or HI. All three of these acids work exactly the same as one another. The only difference is the corresponding halide that's attached. These are all strong acids by definition, and we're going to see how they react with alkenes, and we know, at least for now, that these are going to lead to an addition reaction. That these two groups are going to add across both sides of the alkene. If you walked away understanding that and a little bit about the regiochemistry of where they go, that's all you needed from our pre-lecture video. But now we figure out, and we're going to work slowly together, methodically together, how this happens, so that you could do the same type of work on your own. We're going to start with propene, and we'll react with HCl, and we'll talk very slowly through how these react, and also, more importantly, why they react. We know that this particular compound is an acid. It's a Bronsted-Lowry acid, but it could also be considered a Lewis acid. We know there's a polar bond here. So this compound could be considered a Lewis acid. It wants electrons. Another word for that, a compound that has the property of wanting electrons, is electrophile. Comes from two words, electro from electron, or negatively charged species, and phile from philos, the Greek word for love. This is an electron-loving compound. Correspondingly, the pi bond is nucleophilic, or has electrons, or loves making bonds with nuclei. This would be considered a Lewis base, or the pi bond could be considered a Lewis base, or even a Bronsted base. It can accept a pair of electrons, as we saw in our lecture. So this particular pi bond has an abundance of electrons, right? There's 2 electrons in it. And the acid we've seen react before with real bases like sodium hydroxide by the base giving the acid some electrons, forming a new bond, and shuffling things around. In an addition reaction, it's more complicated than that. We're going to see that both the hydrogen atom and the chlorine atom get attached. The other key thing about this particular alkene that we're looking at is note that this carbon and this carbon are different. Another way that I'm going to refer to these two carbons, or these two sides of the double bond, is that it's unsymmetric. This molecule here is symmetric. Double bond, what's on the right is the same as on the left. This double bond is symmetric. What's on the right is the same as what's on the left. This double bond is unsymmetric. There's 2 hydrogens on this side and a hydrogen and a carbon on this side. This double bond is unsymmetric. This double bond is also unsymmetric, or different. There's 2 hydrogens here. There's a methyl group and a hydrogen here. And in all the examples we do, or almost all the examples we do, I'm going to always specifically pick different substituents on both sides so that we can explore what happens when it reacts with an acid. We're going to get a fresh sheet of paper here. And we'll revisit this problem. We're going to set it up again and work through it slowly together the first time. And we're going to explore what happens when these two compounds react or find one another. This particular pi bond we think of as a base, and we think of this hydrogen as an acid, and so the electrons start moving in the exact same way that we're used to seeing bases react with acids. This is the movement of 2 electrons. Instead of a lone pair, we're now using a pi bond. We're using a pi bond because a pi bond is weaker than a sigma bond. This thing wants electrons. This molecule has lots of electrons, but the only available or accessible ones come from the pi bond, the weakest bond. We're going to start forming a new bond to hydrogen. Hydrogen doesn't want 2 bonds. We show the chloride bond breaking. This is very, very similar to what we did with acid-base reactions. If this was sodium hydroxide and we were doing an acid-base reaction, or water and we were doing an acid-base reaction, these steps would look very, very similar, except the initial pair of electrons would start from a lone pair. We have two possibilities, and we're going to arbitrarily call this carbon Roman numeral 1, and this one carbon Roman numeral 2, and let's explore both of those possibilities. What I mean by this is, this pi bond is going to break, and it's either going to form a new carbon-hydrogen bond at this position, right? The pi bond, the electrons will move this way, we'll form a new bond here, or it's going to break this way, and we're going to form a new carbon-hydrogen bond here. We can't just have a hydrogen dangling off in the middle, not bonded to anything. So this bond's going to break, and it's either going to go here or here. Let's first explore the possibility of making a carbon-hydrogen bond at position 1. So this pi bond is going to break. We're going to form a carbon-hydrogen bond at position 1, and let's see what's left behind at position 2. So in blue, I'm going to draw all the atoms that started on our molecule, and then the new one that I'm going to draw is here. This comes from this hydrogen. This sigma bond was originally a pi bond here. Okay, and that's what this mechanism says. We're going to break a bond, make a new bond, and one possibility is we make the carbon-hydrogen bond in position 1, and that's what we've done here. And if we do this, and we calculate formal charge correctly, there'll be a plus charge here, and this is called a carbocation. And if we're going to be more specific about it, we would call this a primary carbocation, using the same language we learned for radicals. That's why I took time there. We're going to use it throughout this class: primary, secondary, tertiary. This carbon is a carbocation. It's very, very reactive, and it's attached to one carbon. Okay? One possibility. Possibility number 2. We could try the same exercise and think about, well, what happens if this pi bond breaks and we form the carbon-hydrogen bond at this position? So again, in blue, I'm going to draw everything that came from propene. These are all the atoms that came from propene. I'm going to draw our new carbon-hydrogen bond at the second position, and then the carbocation will be at this Roman numeral 1 position. So these two are very, very close to one another. We're just exploring both possibilities in this reaction. Should we form a carbon-hydrogen bond at position 1? If we do, a carbocation will be at position 2. Or should we form a carbon-hydrogen bond at position 2, and then there'll be a carbocation at position 1, and this one would be called a secondary carbocation. And lucky for us, these follow the exact same radical stability trend that we learned about. So when we start these reactions, we're going to explore both possibilities, and then after we draw these on paper, we pick the better of the two, and what we'll do is we're simply going to reject the less stable carbocation. And so when I write this, we're going to translate this into English as carbocation. Carbon cation, or carbocation is how we read it. So whenever we have an unsymmetric alkene and we react it with an acid, there'll be two possible things that we're going to think about. We'll write them both out, then we'll evaluate which one is better. We'll get rid of the one that isn't, and we won't do any more work with it. We're done. Okay? But we continue with this one. This particular compound is sp2 hybridized here. It has an empty p orbital. We're just going to call this a carbocation, and we know that it wants electrons. And now we're going to bring in the anion that left when we did the first acid-base reaction. It would be Cl minus. This wants a positive charge. And what happens next in this mechanism is very, very simple. We're simply just going to react this negatively charged species with a positively charged species. This wants electrons, this has electrons. We move 2 electrons to form a new covalent bond, and the final product for this particular reaction we'll draw now. I've drawn it in such a way that what's in red here are the two species that have added. First, hydrogen adds to the less substituted side. You make a secondary carbocation, and then chloride adds right into that carbocation, establishing the second bond. This is how strong acids add to alkenes. It starts off as a kind of modified new acid-base reaction. You have a new intermediate, the result of forming a bond and breaking a pi bond. And that leaves open the possibility to form a second bond as this carbon now violates the octet rule. It's positively charged. And this part is very, very logical. Negatively charged species combines with positively charged species. Again, luckily for us, basically, that this carbocation stability trend follows radical stability trend. More substitution is better. And lucky for us in this reaction, we explore two possibilities and pick the winner of the two. Those are the key things that we should start right now. This follows this thing called Markovnikov's rule. You might read about it or hear about it later on standardized tests like the MCAT. We're not going to use that language per se because it's not particularly helpful in understanding these processes. What is more helpful in understanding these processes is doing another reaction right away. So let's do that.